in the midterm, this is E1. If I want to write, this is all phasors. What's the IS? These are equations. I prime R plus I phi, right? What is I phi? These are all vector, right? Is IC plus IN. What is E1? This is for currents. What is E1? Is R prime R over S plus JX prime R times I prime R, right? What is VS? RS plus JXS plus E. In the meter, when I asked you to calculate the voltage regulation, most of you we wrote the equation wrong. V prime 2 is R plus JX times I plus V2. Well, most of you put minus. I don't know why. This is not this course. This is just circuit, electrical circuit. You write the KVL here. V prime is this one times current plus V. I don't know why most of you put minus here. That was kind of question in my mind. Why you put it out? That was one of them. The other things I saw a lot in the exam, as I said, I think 1% write it correct. When you have an AC system, it's not like DC, there is a phase also. And I told you all, you have one choice to select. But after that, you have to stick with that. You cannot change the rest. The easiest way, you say, okay, hey, I'm going to get this one with a zero angle. I want my V2 with the zero angle. This is usually the easiest one. But you can select anything you want. You have to stay with that. We said in the exam, we said this current is the point, we said the load is 0.6 lagging power factor. So basically this current is going to be something with lagging. We said lagging. The reason I'm saying it, because nobody did it. Only one person in the class did that one. We are saying lagging power factor. Lagging power factor minus 53 degrees. Go check your papers now. I'm going to give it to you. See how many of you did this one. Minus 53. Lagging power factor. This is your reference. Right? 0. Minus 53. If you put this one 90 degree, this one how much should be? 90 minus 53, right? Whatever is this one, minus 53, this is lagging. We talked about this one. This is a voltage. When we say lag, the current is behind. Right? If this one is 0, this is negative. If this one is, 90, this is a 90 minus this angle. And I'm surprised only 1% in the whole class did this one. 1%. It's very surprising, I don't know why. So here again, you select, usually in this induction machine, usually, again up to you. If you want to select a crazy thing as a reference, select it. There is no problem with that. Usually the easiest way, this one is the reference. For example, I say the machine is a 208 volt, so basically it's going to be 208 over a square root of 3 with a 0 angle. But I selected this one. Up to here was optional. But from here, after, I have to stick with this one. If they say this machine, the power factor of this machine again is, 0.8 leading, this current is going to, if they say leading, is going to be something positive. If they say this machine is the lagging power factor, it's going to be something with a minus that angle. The easiest way is to select this one as a reference. In the transformer, usually you select the load side as a reference. Usually. You can go select here, but your calculation is going to be more width, more calculation. The easiest one is to select the load side as a reference. And you go calculate the rest. Because with this equation you did here, and this one everybody calculated the, just, when you do something, think about it. I remember we had a probability exam when I was in my undergrad. And you know the probability cannot be more than 1, right? That maximum, absolute maximum. And one of my friends, calculated the exam. Looks like he had something like a 2.2 times 0.7. It was 1.4. It's not possible, right? And he just read this one. I remember the professor came to the class and I gave you 0 point. Because if you don't understand the probability cannot be more than 1, you are done. Now, I'll give you the paper. Just go check this one. This voltage, I'm not sure how much was it in the question. But everybody calculated the regulation, not everybody, maybe 70% negative. Negative means this voltage is less. Is it possible? Yes, unless you have capacitor, right? We don't have capacitor. But look at this kind of, these are kind of a simple checkpoint for you when you answer the question. You can look at, so did I do something really crazy or not? You can look at it, and as I said, I'll give you the paper, just look at it, see how many of you calculate the regulation negative. One person put minus 53 in the whole class. I don't know, I think that's the one who got the maximum grade, 95, 96, something like that. Yeah. And, okay. So this is the equivalent circuit of phase A. I'm talking only phase A, usually select the phase A. Again, if you want to go solve phase C, go solve phase C. The problem is you're going to end up with minus 240. I'm going to go with phase A because usually I select my phase A 0. That's the easiest one for calculation, just for calculation, nothing else. This is the equivalent circuit of phase A for induction machine. Okay. Power relation. I'm going to go with the power relation and we are done. And I've solved one example and we are done for today. The homework I'm going to give you Thursday night, it would be covered up to Monday. Tuesday class also, you use the Tuesday class. But Thursday I'm going to cover the last part and if you have time we'll go through some examples, or I go over the homework. Now, power diagram, I don't know what it was. Let's start. The reason we go this way, because in this course, all the time, induction machine we are using is acting as a motor. And in industry also, maybe 90%, 80% of the time, the induction motor, the induction machine, they are used as a motor. In some of the wind power generation, the wind powers, I'm sure all of you have seen those things. They have induction generators also. But mostly, more than maybe 85, 90%, they are used as an induction motor. And that's the reason I use the current this way. Now, this is the terminal of the machine. We plug the machine, see if you look at it, this is the induction machine. Right? And there is a 3 here. This is a 3-phase system. It's going to be connected in a 3-phase source, right? And this is the stator, and this is the rotor. Now I'm not going to put the details here. This is the rotor, and the power is coming to the machine, right? Look at it before we start to write the equation. The power is coming to the machine, goes to the stator, right? In a stator, what we have? We have a copper loss, right? And what else do we have in the stator? Core loss, right? We say the core loss is in the stator. So basically, the power comes to the stator. We are going to have copper loss and core loss here. And after that, this power is going to go through this air gap to the rotor. Right? They call it air gap power or P gap. So basically, the P gap is going to be P in, let's call it here P in. The power coming to the machine minus the stator resistive loss minus the stator core loss. They call it machine core loss. So we are going to have P gap. The power is going through the air gap to the stator, to the rotor, right? When we are in the rotor, Again, what kind of loss we have in the rotor? Resistive loss, right? Or copper loss. And what else? Nothing, right? So the power is going to come out from here. This is the shaft, right? So the power is going to come through the shaft out of the machine. But here, what kind of loss we have here in the shaft? Friction loss, windage loss, right? That kind of loss. They call it rotational loss. They call it rotational loss because the windage and the friction, they are both because of the machine is rotating. They call it rotational loss, right? So after the rotational loss is going to be what? It's going to be mechanical power. This is the power is going to go to the load, right? We call it mechanical power. So basically, quickly I review here. P in is coming here. We are going to have resistive loss and core loss in the stator. The rest, which we call it P gap, goes to the rotor. I'm going to put everything on the board. It's going to go to the rotor. We are going to have a resistive loss in the rotor, right? And the rest is going to go to shaft. On shaft, we are going to have a rotational loss, which is friction and windage loss. And the rest is going to go to the load. We call it P behind, right? Let's start now calculating each one. And I draw the power diagram at the end. How much is the P in or P stator? Let's call it PS or P in. How much is the P in? Somebody tell me. Let's say this machine has a power factor of cosine of P. Let's call it PS, I mean the stator, right? This is a three-phase system. And these values, be careful. These are line values, right? Right?
Phase.
They're phase values, not line. This is three phases, right? These are phase values, right? If the motor is connected to the stator side, here, see, there are three windings. This is the stator winding. We have three windings in the stator, phase A, phase B, phase C. They can be connected as a star, right? They can be connected like this, right? Or they can be connected as a delta. Nobody connected as a delta, always a star. But if in problem, if we say this is delta connected, it's delta connected. So, stator of induction machine, if we don't say anything, it's a star connected, right? A star connected. So basically, this current, which is IL, is still I phase, right? I phase and IL in the star connection, they are the same. But if we give you VL, V phase is going to be VL over the square root of 3, right? That's a three-phase system we went through. So this is the P in. The next one is, let me see what I call it. I call it P stator C, copper stator. PS is copper. I don't know, you can select anything you want, you know. But C is for copper, S is stator. How much is this one? Somebody tell me. How much is this one?
IS squared
IS square times 2, because we have to. This is another thing, kind of makes you kind of sad, You guys should not memorize the equation. For example, in the problem number 3, I said how much capacitance we want for the power factor for the problem 3. You know the Ohm law, right? For resistor. Let's go with the resistor. How much is the power for resistor? V square over R, right? That's, I think everybody knows this. Do you need to cheat sheet for this one? Anybody need to cheat sheet for this one? No. So how much is for resistor? For inductor and capacitor, we know there is no P. There is a Q. How much is Q? V square over either XC or XL, right? If the capacitor is XC, if the inductor is XL, right? I don't think so. You need a cheat sheet, right? For this one also. If you know this one, instead of R, only you should put the X. If the capacitor, you put the XC. If the inductor, you put the XL. Now, when you have it, and we said 100 times, you put it connected as a delta, right? How much is the XC, QC here? We have 3 of them, right? We have 3. And how much is each one? The voltage connected to each one. How much is the VL? And how much is the impedance? XC. Do you need a cheat sheet for this one to memorize it? No, really, I'm saying, the reason I didn't give you cheat sheet because there was a very basic equation, what you need to solve the problem. Instead of confusing you to spend like 2 days to fill out the one sheet, to try to put everything on that sheet, I think that you don't focus on your homeworks, you read them to understand them. But this is the equation you need, all. You need for that exam. Okay. Go check this thing. Now when I'm saying when I give you the paper, check all the things I mentioned. Look at your paper to see how many of you have made a mistake on this one. I'm sorry. So we talked about the input power to the stator. This is the copper loss in the stator. And what else we have? Peak core loss we cannot calculate. That's from the text. We'll talk about that one later. Like core loss in the transformer, right? So we have a peak core. I call it. I don't know what. Oh, if we have this RC, we can calculate. But usually you don't have the RC value. But if we have the RC value peak core, how much is it? 3 RC IC to the power of 2, right? That's the core loss. Now, we came up to this point, right? We finished the stator, going to the rotor, right? This is the power is going through the air gap to the rotor. We call it P gap. How much is the P gap? It's P in minus P SCU minus P core, right? That's correct. But this power, how much is the P gap? Somebody tell me how much is the P gap. P gap is coming here. Can somebody tell me how much is the P gap? P gap, exactly. This is this part, right? This is the gap. Here was the stator. We went to the rotor, right? The power going through here is going to be 3 times this resistor and this current to the power of 2, right? Because this one doesn't dissipate any active power. This is an X, right? So P gap is 3 times is a P gap. How much is the rotor power loss? P rotor C. Somebody tell me. How much is it? Forget P gap. No. The rotor has a resistance of RR, right? Or R prime R in this case, right? It's going to be 3. Is it correct? If the current in the rotor is I prime R, and the resistor of winding is I prime R, so 3 times that is going to be the rotor copper loss, right? Like a stator copper loss. The resistance is RS, the current is IS, so it's 3 times RS IS to the power of 2. So what you see here, tell me. How much is PR? Is it correct? Right? P rotor copper is S times P gap, right?
Why is it no S? Why isn't it R prime R for S in the copper one?
No, that's the what? I'm going to correct, not correct, I'm going to develop this circuit a little bit more. This side is a stator, right? From here is the rotor, right? And between a stator and rotor there is an air gap, right? I call it gap. The power coming from here is going to be the power is dissipated here, right? But in the rotor, how much power loss do you have? In the winding of rotor. If the resistance of the winding is R up, it's going to be Ri squared, right? We have three of them, 3 times R times I squared. But I'm going to develop this circuit a little bit more. Give me a little bit more time. Now we have the P copper C. The question Shaw asked, it doesn't look very kind of, matching this circuit. So let me redraw this circuit. Put it this way. I'm going to put it this way, because I want this one to make sense a little bit more. I'm going to put it this way. And tell me if it's wrong. This is the RX, XS, IS, RC, XM, IP, IM, IC, I prime R. I'm going to put this one R prime R, X prime R. But look at here. This I'm going to for now I'm going to call it RX. Just let's call it RX. This one plus this one, you don't have to write these things. But R prime R plus RX, these two, add together, should be this much, right? Should be this much. And this way, this circuit is going to be equal to that circuit, right? So let's put R prime R. This should be equal to this. So how much Rx should be? Should be R prime R. This one is very good. This one is going to be 1 over S minus 1, or it's going to be R prime R. Is that correct? Yes, that's correct. So basically here we should have a R prime R times 1 minus S over S. And I'm going to put this variable. Y, and what's the Y variable I put there? Load change, exactly. This one is going to exactly, remember what I said? I said P in P resistive loss, P core loss, P gap, rotor resistive loss, right? And after that it's going to go to the shaft. This one is going to show me the power is going to the shaft, right? P in minus the stator resistive loss, minus the stator core loss, minus rotor resistive loss. The rest is going to be what? From here, it's going to be P mechanical. Oh, I don't know what they call it over there. P mechanical, right? But P load is going to be mechanical minus rotational, right? Rotational loss. The reason I put this one variable, if my load changes, R prime R is going to change or not? R prime R. No, that's winding. The resistance of that one is fixed, right? But S is going to change. If you put a no load, there is no load, S is going to be almost 0. Very, very, very close to 0. But if the load is heavy, S is going to increase. It's going to become 0.2%, 2%, 3%, 5%. And if you put too much load on it, S is going to be 1. Basically, S is 1, means there is no load anymore. You are not pushing anymore current to the load. So this is representing the load, the variable load in the system. So that was P gap. P gap is coming here. This is a gap here, right? This is a gap, right? P gap, we have the resistive loss in this rotor, and after that, this is the P. I'm not sure what you call it. I think I call it developed power. Let's see what I call it. P mechanical. I call it P mechanical. So now, how much is the mechanical power? Which is this part. Somebody tell me, how much is the mechanical power?
I prime r squared times r prime r times 1 minus s over s.
Say, P net. How much is it?
This is I prime r squared.
I prime r, right?
Yes.
To the power of 2
2
times
r prime r times 1 minus s over s.
over s and time
3.
because we have 3 of them, right?
Why do we have 3?
It's a 3-phase system, right?
I thought it is the loss from the shaft rotating. If there's only one.
No, that's after this one. This is P mechanical, and let's say if you are going to show it here, this is the shaft here. Now we have the P rotational. P root. And that's what is going to be P load, right? After that, it's going to be P load. Now P load is going to be P mech minus P road. Road is a rotational loss. Rotational loss is because of friction and because of windage loss, right? Now let's draw the power diagram. We had a P in coming, right? Or P in or PS, whatever you want to call it, right? What did it lose first? P stator copper, right? What did we do next? What did we lose next? P core, right? Basically, this one is coming in, part of it is going here, part of it is going there. So, what was this one? What did we call this one? P gap, right? And after a year, what did we lose again? P rotor copper. And what did we call it here? This is the P mech, right? And what did we lose after here?
P rotational.
P rotational. And what is here?
P load.
P load. Right. And P load at the very end. P times omega, right? Electrical torque times omega. Usually we ignore this P rotational because we don't know how much is it. Basically P mechanical is the P load. We ignore this one. Or some people they call it developed torque. If you see here developed, power, they call it developed power. Is this one. Yeah, most of the time we don't give the number for P rotational P. Just you assume that one is 0. This is a power diagram. If we tell you how much is the efficiency of the system, how much is it? Right? And just I want to mention this one. We call this one, this is a load. We call it load resistance, right? This one. Here. We call it load resistance. So, just finish a quick example and after that we'll go to your start. Initially it said we have a 3-phase, and if we don't mention 3-phase, it still means 3-phase. If they say we have an induction motor, that's 3-phase by default. Or they said we have a 3-phase induction motor, so we have a 3-phase induction motor, it's a 60 hertz machine, 4 poles, and this is what we have. And the stator winding, RS per phase. Everything is per phase. 0.056 ohm per phase. Sometimes they don't write the per phase, but it still means per phase. Ohm per phase means each phase has this much resistance. It says calculate the rotor power dissipation. We want to know how much is the P rotor. P P rotor loss. We want to calculate P rotor loss at a speed of, if n is equal to 1738 RPM. So when P in is 47.4 kilowatt and IS is 76.2 amps. Let me go through the example what it's asking. It's saying we have an induction motor, it's a 60 hertz, 4 pole, and the stator winding resistance is 0.056 ohm. If the input power of the motor is a 47.4 kilowatt and absorb this much current, 76.2 amps, we have, I don't have to say it here, 70.62 amps is coming here, is giving me the amplitude of this current. It doesn't talk about the phase, right? This much current coming here, and if the speed of the rotor is this much, how much is the rotor loss? What's the rotor loss? Let's understand what we are looking for. What is the rotor loss? This is the copper loss in the rotor, right? We don't have any other loss in the rotor, it's the copper loss, right? So, if I want to calculate the copper loss, should I use this equation? Why?
The only loss in the rotor.
No, you cannot. Why? You cannot. Why? We don't know how much is our prime R, right? Our prime R. We don't know how much is that one. How about this one? Can I use this one? S I can calculate, right? I have the speed of machine, I have the number of poles, I can go calculate the S. So basically I can calculate P gap, I'm good, right? How about P gap? Come here. How much was the P gap? Was the P in minus PS copper minus P core? P core didn't tell me I'm going to ignore it, right? We don't have that one, so put it in. Let's go calculate. I'm going to write it here. First, let's calculate the NS. How much is the NS? Right? 120 times 60 hertz over how many poles? 4 poles, right? 4 poles, right? So basically, it's going to be 1800 RPM. How much is the S asleep? Is NS minus N over NS. So S is going to be 1800 minus 1738 over 1800. So basically it's going to be 0.034. I calculated S. Now I need to calculate the P gap. If I know how much is the P gap, I time it by S, I'm going to get P rotor, right? I still call this for P rotor C. So let's calculate the P gap. P gap, as we said, is P in minus P stator copper minus P core. It didn't say anything about this one. We assume this one is almost zero. We don't have a number, right? How much is the P in? P in is 47.4 kilowatt minus. How much is the PS? 3 times. How much is RS? I have it here. 0.056 times. How much is IS? 76.2. I need to divide this one by 1000. Why? because it's a kilowatt, right? Or you can write this one in a watt and flip it out. So if you calculate this one, heat gap will be so how much is the P rotor? P rotor Cu is going to be S P gap. How much is S? 0.034 times 46.425. So P rotor copper is equal to 1. You're done quickly.